Okay, so now let's welcome our next speaker, Akash Banerjee from Presidency University, Kolkata, India. The title of his talk is Advancing Local Alpha Fractal Interpolation from Compact Intervals to Standard Function Spaces. So, I would like to welcome you, Akash. So, over to
Thank
you.
you. Yeah, sure.
Your slides are not visible. I hope you know it.
Okay. Right now,
Yes, okay.
is it visible? Okay.
Yes, perfectly fine. Thank you.
Okay. Okay. First of all, thank you to the organizers. Thanks to the organizers to letting me this opportunity to give this talk. So this is a work. This talk is based on a joint work with my one of my supervisors, Mohammad Nasim Akhtar and Ma'am Navaskas ma'am. So the title of this talk is Advancing Local Alpha Fractal Interpolation Functions from Compact Intervals to Standard Function Spaces. So this is the overview of my talk. First of all, I will introduce what a IFS is. Then I will talk about the basic construction of fractal interpolation function. Then I will give a basic overview of alpha fractal functions, then local fractal functions, and ultimately I will introduce the uh, main topic of this talk, that is local alpha fractal functions that we have constructed by using ideas from alpha fractal functions and local fractal functions. So alpha fractal functions, they are introduced by Navaskas ma'am, and local fractal functions are introduced by Massapost. So we somehow combine this, in some way we can say that we combine these two ideas to form this new concept of local alpha fractal functions. So basically local alpha fractal functions are in some way local generalizations of alpha fractal functions. So alpha fractal functions, basically what they are basically fractal functions which approximate certain continuous functions. Okay, so if you give a continuous function over a compact interval, then by the machinery of alpha fractal functions, it is possible to form fractal functions, basically say a function which is, say, nowhere differentiable and continuous, obviously, so that these two functions, this fractal function and the given continuous function, are very close to each other in some norm. Here they used supremum, and so we generalize this idea to mainly so alpha fractal functions, basically they operate globally. So we somehow, in some sense, we generalize this idea in a local sense. Okay, so let me go to the details first. So then last of all, I will talk about some generalization, how we can more generalize the idea of local alpha fractal functions, and some I will discuss some open problems. So IFS is just a topological space and a collection of continuous functions defined on the space, a finite collection. And throughout this presentation, mainly X will be a complete metric space, and we can also define this Hausdorff metric, which looks like this: dh of AB, uh, uh, which just gives a distance between two compact sets. And with this metric, the space of all non-empty compact sets forms a complete metric space. And and, and uh, then we can define this operator capital F, which defines like this: capital F of S. S is a non-empty compact set. The image of S is nothing but the union of the images of S under Fi's, and this F is called the Hutchinson operator, and 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 particular non-empty compact set capital S is called an attractor of this operator if S is a fixed point of this function. Now I will directly go to fractal interpolation functions. So fractal interpolation functions, they are introduced by Barnsley. So basically, traditionally interpolation functions are smooth. Uh, so uh, so fundamentally they lack the potential to interpolate real world data like signals or maybe clouds, maybe or many there are many examples of real world examples where um, traditional interpolation functions are unable to somehow model those things. Okay, so that's why Barnsley introduced this fractal interpolation function. So but the construction goes like this. So you start with a set of real numbers, a finite set of real numbers, and corresponding to those real numbers, we we uh, we consider a data set. Here we denoted that with Tn comma xn, and then we use a set of contractive homeomorphisms. I'm not going into the details, but this homeomorphism, just what they do is they take the whole interval, that is t0 comma t capital N, the whole thing, and contract it into a smaller sub interval for, say, for a small n, that is t n minus 1 comma t n. That's all. And then we also consider this capital Fn's. So they are also contractive mappings. They are contractive mappings on this uh, subset of this square. Kind of, we form a square or a rectangle, to be precise, which is defined by this capital I. Capital I was the main interval t0 comma tn, with we product it with another closed in interval with some suitable real numbers a and b. And capital Fn's are functions, continuous functions from this k to this interval ab, which are continuous in the second variable, and where these alpha n's are very important. So these alpha n's are contraction ratios, which are in -1 and 1, which ranges between -1 and 1. And this so this the contractive homeomorphism that I mentioned earlier, this aliens satisfies this join up conditions, and also this fn's also satisfy the join up conditions. And so these join up conditions are basically there to ensure that the fractal interpolation function, that output, the final output, the fractal interpolation functions remains continuous. Okay, and with help of these two functions we define these wn's. They are just functions from k to k, which are defined like this. So Barnsley proved that this k as a if we take k as the basic topological space, and on that if we take the functions wn, and they form a ifs, and this ifs has a unique attractor g. And mainly what he have proved there, which is more important, that is this g, this attractor g is a graph of a continuous function h. H is a continuous function from I to this interval AB, such that this H actually interpolates the given data set that we have assumed in the beginning. This small h, this function is called a fractal interpolation function, corresponding to the IFS k comma wn and the given data set. So this is a particular example of a fractal interpolation function corresponding to this data set I comma sine of 6i, where I is just this 3.0, 1 half and 1. Okay, fine. Oh, so also this fractal interpolation function can also achieved through function operators on fixed point of operators on a particular function space. That function space here we denoted it by the script G. So this is a collection of continuous function f from I to ab such that the end 2 points actually they interpolate. So f of t0 is x0, the first point, and the f of t capital N equal to x capital N, that is the last point. So on this space becomes a complete metric space with respect to the uniform norm, and we can define a particular operator which is known by operator. This RB operator in this case it is defined like this, and we can show that this T is a contraction mapping on the complex metric space and with respect to the uniform norm. And by Banach's fixed point theorem there will be a unique fixed point, and this particular fixed point is exactly that H that we have seen earlier, that is the fractal interpolation function. Okay, so now moving on to alpha fractal functions. So alpha fractal functions build up on the on this construction of fractal interpolation functions. So here uh, let me okay, yes. So as we have seen, we have taken ln's and fn's some contraction mappings on some certain sets. So here what Navaskas ma'am has done is she had taken ln and fn in a very particular form. So ln is this linear function ant plus bn, where a and bn are suitable constants which can be determined from the join up conditions that satisfies satisfy ln and fn. And fn also, fn looks like this. Alpha n are just the contraction factors of or the contraction ratios of fn, and so fn looks like this: alpha n into x plus qnt, where this qn of t is a continuous function from I to ab, and it is chosen in such a way that capital Fn satisfies the join up conditions. Okay, and a and bn can also be determined. And so in particular, Navaskas ma'am what has considered considered qnt as this: the qnt is equal to, so if is a so first of all we take a continuous function f which we intend to approximate with the help of a with the help of a fractal functions. Okay, so first we take a continuous function f on that interval t0 comma tn, and so q1t is then defined like this, which is f compose lnt. Lnt is this ant plus bn minus alpha n into bt. Alpha n is this, the alpha n are the contraction ratios of fn, and this bt is called the base function. So bt is a continuous function on I, and it also satisfies the also interpolates the endpoint. So b of t0 x0, b of tn equal to xn. And obviously there is another condition, which is b cannot be equal to f, which is not mentioned here. Yes, I have mentioned here. B cannot be exactly equal to f. Okay, so now with this particular ln, fn, and this qnt, so again that the RB operator T is a unique fixed point, which is called the alpha fractal function associated to f and with respect to the base function b and the particular partition that we have taken t0, t1, t2, tn. And this alpha is actually a vector which is formed by this alpha n. So alpha is a n tuple, capital N tuple, which looks like this: alpha 1, alpha 2, alpha n. Okay, fine. So this is a particular function fx, which is 5 e to the power minus 2x into cos 15x. This is the graph of that function in the interval 0 and 1. And this is the figure of the a particular alpha fractal function associated to this f, which we denote by f alpha. So as we can see that the global structure of the function remains almost same, but this function is not at all smooth. So this function is nowhere differentiable, whereas the original function was continuous. So now we introduce what local fractal functions are. So as I have mentioned earlier, Peter Massapoust introduced local fractal functions, and they are just localization of fractal functions. Okay, so he introduce this concept on a very general setup, like in a so x the base space x is just a non-empty connected set, and then he taken xi's. So xi's are finite collection of family of non-empty connected subsets of x. So he just partitioned in not partitioned, or he had taken non-empty connected subsets of capital X, and then again, so these are like the contractions that we have mentioned earlier, ln's. These are just generalization of the ln's. So these are ui's, which take this non-empty connected subsets capital xi to x. They are injective mappings, and this these are not generalization of ln's are contraction from the whole interval to a sub interval. So this is not like that, this is the opposite of that. So ui takes a smaller subset xi to the larger set capital X, and so these are these uis are injective mappings, which is a property that this ui of xi forms a partition of x. So we can say that this ui of xi's are the generalization of those smaller sub intervals tn minus 1 comma tn. And then we take another complete linear metric space. So this metric space has to be linear, and then we take the metric b cap or sorry, the space b xy, which is the collection of all bounded functions from x to y. On that we take the sup metric. So then we take vi's. So vi's are functions from xi cross y to y. So these are just generalization of those fn's, capital fn's. Okay, so again, as we have seen for fn, in this case also vi's are contraction mappings in the second variable. Okay, and then we can define the generalized form of rb operator. So rb operator phi is an operator from this function space to this function space, and this is the particular form, which I'm not going in the detail. So, and this we can show that this particular operator is a contraction on the complete metric space capital B, and the by Banach's fixed point theorem there is a unique fixed point, and that fixed point is called a local fractal function corresponding to the corresponding to uh, generated by phi, sorry, generated by phi. And this is a graph of a randomly generated local fractal function. So as you can see, these red dots are they represent the discontinuity. So this function is a discontinuous function, which is in contrast to the fractal functions and alpha fractal function that we have seen earlier. Now we come to the the construction of local fractal functions. So here what we have done is we have taken the interval t0 comma tn and partitioned it into this 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 bounded intervals, okay, x0 comma xk, and we have taken some data set xi comma yi, and let capital AI be a collection of non-empty connected subsets of A that we need. Um, and they are taken in such a way that x0 belongs to ai for all I. So the first point of the interval x0 has to be in all of these connected subsets. So connected subsets means just closed intervals or open intervals, and xk, the last point, has to be in the last set, a capital K. And then we have taken lambdas as required. They are injective maps from capital ai to I, which satisfy the following properties that we need. And also this lambda is has to satisfy the join up condition. Then we taken the function space bounded, the space of all bounded functions from a to r. Then we have taken a subspace of that space, which is the set of all bounded functions which interpolate the endpoint. So h of x0 is y0 and h of x equal to yk. Then we have taken alpha is. Alpha is not merely just constants, they are now bounded functions from ai to r in such a way that the sup norm of alpha I is less than 1. Okay, between 0 and 1. And alpha, we have taken alpha as the maximum of all these sup norms of alpha I. Then this is the theorem. This is the main theorem. So for a fixed g and base function b belongs to this h cap script h, where all the bounded functions were, which interpolate the endpoints. And for a given collection of non-empty connected subsets ai, and collection of corresponding collection of injective maps lambda I from ai to a, there will be a unique function g alpha, which also belongs to h, so which is also a bounded function, which satisfies this self-referential equation. So g alpha actually approximates g, and this g alpha is called the local alpha fractal function associated to small g and with respect to the base function b, and the collection of all those connected subintervals, that is capital P, and corresponding injective maps, collection of injective maps capital F. Uh, so we can also prove that g alpha interpolates g at these points xi, the given data points, and also g alpha satisfies this particular g alpha minus g satisfies this inequality, from which we can show that if alpha is close to 0, g alpha is a very good approximation of g with respect to the sup norm, obviously. This is a particular example of a local fractal function. So the blue one is the old function that we have seen earlier, 5e to the power minus 2x cos 15x, and this orange one is a particular local fractal analog. So in this case, we have taken the construction in such a way that the output is a continuous function. And this is again another one of the same, and this is another one. So we can see that this particular orange function, that the local fractal analog of f, is not continuous at all. So in this local case, we can construct the particular subsets and injective function in such a way that the output is not a continuous function. And this is another example of that. There is a side by side comparison. So last of all, the last phase of my talk. So there are some theoretical challenges in this construction. So first of all, the existence and uniqueness of the G alpha is established primarily on compact intervals, and the framework heavily relies on supremum norms on the space of all bounded functions. So the suggested generalizations are, we can generalize this idea to more general, more useful function spaces such as the Lebesgue spaces LP, the Sobolev spaces, where there are particular advantage and disadvantages also. And also we can generalize the idea to from compact intervals to say non-compact intervals like semi-infinite intervals, and ultimately to the whole real line R. And again we can also generalize the idea from R to R2 and R3 and so on. Um, so these are just the open problems, operatory extension. So where we can try to prove the contractivity of T with some extra conditions, maybe on LP or this Sobolev spaces, the domain extension, and the other thing. Okay, so these are the references. This is the main paper, local alpha fractal interpolation function, and these are the other references that I have used. And thank you for listening. If you have any questions, you can ask now.
Okay. So thank you, Akash. Now I would like to request to the audience if they have any question for Akash. So if not, let's thank the speaker.
Yeah, thank
So
you
our
so much.
next talk will start in 2 minutes.